Hi, my name is Travis and I'm here with my partner Viraj. We will be discussing the Zues laser engraver. The background image you can see on this foil is the finished laser engraver system that we are talking about. This slide shows the content that will be covered in this presentation. I will be covering the introduction, the execution timeline, and the hardware. In the hardware section I will cover the frame assembly, the laser module, and the control box. At this point, Viraj will take over and discuss the software of the system and finish with a conclusion. Computer numerical controlled machines, or CNC machines for short, are becoming more popular in today's world. These machines are cheap, precise, and produce an identical item every time, which makes them perfect for manufacturing. The main goal of this project was to design, build, and operate a CNC laser engraver. The embedded system required a great deal of electrical, mechanical, and software engineering to successfully transfer a digital image onto a wooden media. This slide shows the timeline of the laser engraving project. The project took around 71 days from start to finish. This slide shows the major milestones achieved, which mainly came once the parts were delivered and the mainframe was constructed. This timeline also shows that there are multiple developmental phases and testing phases. These will be discussed later in the presentation. We'll now discuss the hardware section of the embedded system. This consists of the frame assembly, the laser module, and the control box. This first slide shows the system's frame. This frame is built out of extruded aluminum V-channel rails with dimensions of 20 by 40 by 500 millimeters. The rails are connected using corner brackets with nuts that fit within the V-channels of the rails, securing each rails to each other. The Y-axis rail is free to move along the X-axis rails, and the laser module is free to move along the Y-axis rail. This gives the system its two-dimensional movement. Continuing the frame assembly, there are 4 other components that need to be discussed. The custom built out of 1/8" aluminum plate. These mounts are used to hold the motor and axle assemblies. Each mount has 5 precision holes milled for the motors and 3 for the axle assemblies, which is in a triangle configuration. And the X mounts are, there are 2 channels which are for the adjustable Y-axis. The motors used are 2-phase 1.8-degree stepper motors. There are 2 for the X-axis and 1 for the Y. Each motor rotates a timing belt which transfers the rotational movement to linear movement. The axis assembly is configured in a triangle shape which gives the most stability with the least amount of axles. There are 2 axles that run along the top of the rail with a single axle along the bottom that provides support. Last, the timing belt used is a GT2 belt with a pitch of 2 millimeters. These belts fit within the V-channel of the rails and come up through the top 2 wheels and around the motor timing pulley. The timing belts are then anchored at both ends of the rail. This slide shows the complete laser module. On the image there are boxes which indicate the part of the circuit that is seen in the schematic. The main part of the module is the 2-watt 445 laser diode marked by the blue box. The max current of this laser diode is 1.8 amps, which is controlled by the laser diode indicated by the purple box. To control the laser on and off, a high current NPN BJT was used, which is marked by the red box. And finally, the Arduino GPIO pins outputs are 5 volt at 40 milliamp max. This output is too high for the NPN transistor. Therefore, a current regulator was used to reduce the current to 30 milliamps, which is marked by the orange box. Last is the control box. The control box holds the major electronic components of the laser engraver. Next to the image is a model of how all these components are connected. The Raspberry Pi is the start of the system, is connected to the Arduino Uno, which is connected to the G-Shield. From the G-Shield, the signals is sent to the motors and the laser module. Powering the system is an LED 24-volt 15-amp power supply located underneath the control box and is attached using industrial strength Velcro. The G-Shield runs directly off the 24 volts. There are 2 buck converters where they're used to reduce the 24 volt to 5 volts for the Raspberry and 9 volts for the laser module. The design of this control box also allows it to be detachable from the laser system. This is done by having all the input and output wires going through a 24-pin connector. This ends the hardware portion of the presentation, and I'll give control over to Viraj.
Hi, my name is Viraj Padte, and we will continue with the presentation to discuss about the software tools needed to work with the laser engraver. Since the system is fundamentally a CNC machine, let's discuss some about related conventions to CNC machining. The numerical control is a method of automatically operating a manufacturing machine based on a code of letters, numbers, and special characters. G-code programming, originally referred to as address programming format, is a popular standard used for sending commands to the CNC machine. Next, we move on to the GRBL firmware. The GRBL is an open source firmware used with the Arduino platform for implementing the G-code interpreter. Implementation requires configuration based on the mechanical parameters of the system. A configuration modification was done to range the spindle values between 0 to 255 so as to use them for the PWM generation. Next we go on to image to G-code conversion process. The entire process was done using a core element which is Inkscape. Inkscape is an open source graphics application which has a vast library of plugins for G-code tools. However, running and processing using Inkscape on a Raspberry Pi would make the process of conversion slow. A solution to this was developing a Zenity based light GUI interface for Inkscape, which made it possible to achieve conversion of standard 10x10 mm image in about 7 seconds. Next, we move on to the last element, which is the G-code sender. This essentially is a simple serial read-write application used for sending G-codes to the engraver. The GUI is an open source implementation of the GRBL controller project. The GUI is designed in Qt and modifications to the project were made to customize it to match the engraver's workspace. Next, we move on to a video illustrating the entire workspace workflow for using the engraver. Here we will see how the CSU RAM's logo is engraved onto wood. This is the CSU RAM's logo. We go on by first starting the image to G-code conversion tool. It asks us to select a particular image, which is in this case rams.svg. We then go to an options selection menu where we select an 8-bit grayscale conversion type. We have 4 conversion types. We then go to the G-code sender where we first open the COM port. Then we go on to choose the file which was converted to the G-code. And once the file is loaded, we click on begin in order to start. It takes a initial time of 3 seconds for the conversion process to start. Once the process starts, we have put now a time-lapse video to show the exact real process of the image getting burned onto a piece of wood. This will result in an output which will be now shown. Now we go on to the testing and verification process. Each of the project development phases were complemented by testing phases. This was crucial in order to ensure that we progress on the project as per the planned tasks to achieve each milestone. The first phase of testing comprised of testing the motor drivers and the laser driving circuit. One of the major challenges we faced was to design a circuit needed to drive the laser diode using the PWM pins. In the second phase of testing, we worked on testing the positional accuracy of the X and Y axes. We also worked on finding the precise value of translation parameter which maps the machine space coordinates to the workspace coordinates. Throughout the project, we also have done some miscellaneous testing. It included working on the heating problem of the laser and handling the smoke produced during the burning process, which was heavily impacting the precision of cutting. Next, we move on to the cost analysis of the project. We spent about $800 for completing the project. The slide clearly indicates the segmentation of the budget. It is clear that most of the funds were spent on the electronics. Well, it is obvious as we have used a lot of rapid prototyping platforms. In the future, we plan to work on the system to make it more robust. We already have planned on working on the mentioned hardware and software aspects of the project. Finally, I would like to conclude by saying the goal of this project was to design, build and operate a CNC laser engraving system. In the end, the system was successful in engraving images and photographs into wooden media. Through this project, we learned planning, testing and teamwork. A lot of aspects of embedded design were explored while building this complex electromechanical project. Thank you.